Can you just confirm that it's fine? Okay, so let's start. Yeah, welcome everyone to the sixth talk in this Theory Matters series. We're very happy to have Mathew give this talk. Just to give a brief bio, he received his master's and PhD degrees from the Department of Computer Science and Automation at the Indian Institute of Science, Bangalore. He did two postdocs, one first at Dalhousie University in Canada and then at the University of Haifa, where he worked with Martin Golombek, Ilan Newman, and Yuri Rabinovich. He was then an assistant professor and subsequently, so he was an assistant professor at the Department of CSE at IIT Kharagpur before joining IIT Hyderabad, where he's currently an associate professor. So yeah, thanks Rogers for kindly agreeing to give this talk. So he'll be speaking about conflict-free coloring on closed neighborhoods of bounded degree graphs. I guess, yeah, as the title speaks, his main interests are in combinatorics and graph theory. So yeah, just before I hand it over to you, I guess if as always, if people want to ask a question, you can either unmute yourselves or you can just put up the question in the chat box. So Rogers, it's okay if I interrupt, if one of us interrupts you in between? Okay, yeah. Okay, yeah, over. Yes, perfect. Yeah, okay, thanks. Over to you.
One, two, three, four, five given to you, and the notion of conflict-free coloring is basically color the points of this universe with minimum number of colors, such that you take any hyperedge or any set in the second row. There is some color appearing exactly once in that set. So let's look at this. So if I give 1, 2, 3, 4, and 5 different colors, I mean each point a different color, then naturally this will be satisfied. But what we are interested in minimizing the number of colors. So here, if you look, we have a coloring where points 1 and 2 get red, 3 and 5 get blue, and 4 gets an orange color. And you can see every set or every hyperedge in this. So it's a hypergraph where these hyperedges are basically subsets of that vertex set. And in the first hyperedge 1, 2, 3, you have 3 getting a distinct color, which is blue, from that of 1 and 2. 3, 4, you have 4 getting a distinct color. In fact, 3 is also getting a distinct color. It's a two-sized hyperedge. But if you look at 1 to 5, you have 5 getting a distinct blue color compared to the red colors which 1 and 2 are getting, right? I think you can see my mouse pointer as well. Okay, so this is a conflict-free coloring here, that every hyperedge has some point getting a color which is distinct from the other points inside that hyperedge. Okay, these are your hyperedges. 1, 2, 3 is a hyperedge, 3, 4 is another hyperedge, and so on. And naturally, the question is minimizing the number of colors required to color the points in this V. So here we have used 3 colors, red, blue, and green, such that every hyperedge E contains a point whose color is distinct from that of every other color, every other point in color of every other point in that hyperedge. So I hope this definition is clear to everybody. So what is our objective? We want to minimize the usage of minimize the number of colors used, so that every hyperedge or every set in this family has some color appearing exactly once in it. Now, yeah, this is that slide where we talk about an application in wireless communication. So at least this is what the papers in this domain claim. So if you take these red, blue, green circles as like the coverage area of various mobile towers, so T1 is the coverage area of the first mobile tower, T2 the coverage area of second mobile tower, and so on. And so you can construct a hypergraph where T1, T2, T3, T4 are the vertex set, or basically the universe, and the hyper edges are basically, you take any point in this 2-dimensional plane, and you take that point and see how many in the vicinity of how many towers is this point, like in which are the towers in whose coverage area is this point. So they form the hyper edge corresponding to that point. So for instance, corresponding to this point is in the coverage area of just T1. So you have this hyper edge with only T1. Whereas if you look at this point, it is in the coverage area of T4, T2, T4 and T2. So you have a hyper edge with just T4 and T2 here, and so on. So this point is in the coverage area of T2, T3, and T4, and you have a hyper edge with T2, T3, and T4. And now a conflict-free coloring here is the same as asking for the following, that at any point a person standing there has some tower communicating to it, or a device there has some tower communicating to it, that device in a distinct frequency. So you have this. So if you look at T2, T3, T4, which is basically this point has this point in fact has all the 3, they're red, blue, green. So yeah, somebody communicating in a distinct frequency, so that that's the requirement here. Okay. So and the minimum number of frequency, minimum number of this required to do this. That's what our objective is, like conflict-free coloring is, right? Okay, so yeah, so as I said, it's motivated by applications in wireless communications, and so it has been extensively studied, and so for people in wireless communications, probably this the study on geometric graphs, where actually like graphs, unit disk graphs, and these kind of geometric graphs, which are maybe close to this practical application, maybe of more interest. And people have, the general problem is on hypergraphs, and also they have studied it. People have studied it on hypergraphs induced by neighborhoods in graphs, which is what we are also going to look at. One of these variants is what we are going to look at in this talk, and also some other kinds of hypergraphs. And what would be more interesting to this to the wireless communication community, maybe these hypergraphs that naturally arise in geometry. Okay, but you can actually look at the survey paper for more results on that. Okay, so let's look at the problem that the variant of this hypergraph, variant of this conflict-free coloring that which we define on graphs, which we are going to look at. So here you have a graph, and so let me define what is the closed neighborhood of a vertex. So the closed neighborhood of a vertex is basically all its neighbors plus itself. So if you look at the vertex A here in this graph, so I use this notation to define denote its closed neighborhood, and its closed neighborhood contains its neighbors basically E, F, and G, plus itself, plus A. So AEF, sorry, EFB and A. Okay. And if you construct a hypergraph whose vertices are basically the vertices of this given graph. So you're given a graph right now, and you're going to construct a hypergraph out of it, where the vertices are basically the vertices of the graph itself, whereas the hyperedges are basically close neighborhoods of each vertex. So one of the hyperedges would be this AEFB, because it's the close neighborhood of A. Now another hyperedge would be BAGC, which is the close neighborhood of B. The next one would be close neighborhood of C, D, and so on. So that's the collection of hyper edges. And then the same question you can ask, right? Like you want a coloring where, I mean, now what about this conflict-free coloring of this hypergraph? This hypergraph that we constructed out of this graph, out of a given graph, from the close neighborhoods of each vertex, where the close neighborhoods of each vertex form a hyperedge. Now the conflict-free chromatic number of this hypergraph. So this is what we call the CFCN coloring, or basically conflict-free close neighborhood coloring of a graph. Or if you don't want to go into hypergraphs and you only want to focus on graphs, it's basically you take any vertex in its close neighborhood, some color should appear exactly once. So if you look at vertex A, the color of F, which is blue, appears exactly once in its close neighborhood. If you look at vertex H, the color of vertex C, which is orange, appears exactly once in its close neighborhood, because every other neighbor is blue in color. So here I have given a coloring of this graph using just two colors, and this is the conflict-free coloring of conflict-free close neighborhood coloring. Okay. So this is the definition, formal definition here, and this is the notation that we are going to use. So chi CFC, and chi is generally the terminology used for notation used for chromatic number. So this is conflict-free. CF stands for conflict-free. CN stands for close neighborhood. Okay. So we are interested in this, the minimum number of colors required to color the vertices, such that every vertex sees, for every vertex, there is a color that appears exactly once in its close neighborhood. Now, first thing is that this conflict-free chromatic number is at most classical chromatic number for any graph. So what is classical chromatic number? You want to color the vertices of a graph such that if two vertices U and V are adjacent, they get different colors, right? Now, any classical coloring is also a conflict-free close neighborhood coloring. You can actually go back and verify that. So that's an up. Yeah. Anybody has a question? Yeah, it's different from saying that each hyperedge has more than one color. That is a coloring of a hypergraph, but there's the frequencies of the colors can be, I mean, let's say a hyperedge sees two colors, but each color appears like that's possible. Yes, yes. Yeah, here we want some color appearing exactly once in that hyperedge. Okay. Is there any other? Maybe Subruk is here. Maybe Subruk. Do you remember of any? I think application is just.
No, I don't recall any specific applications. Let me try to think, and maybe I'll update.
Yeah. Oh, okay. That could be there. I think maybe within combinatorial. I mean, it may be. I mean, bounds here may serve as some bound. I mean, serve in getting some bounds for some other combinatorial problems. That could very well be there. I mean, I don't know of anything right now, but immediately. But okay, so this is and it's decision problem whether you are given a graph and whether its conflict-free close neighborhood chromatic number is at most k, is NP complete. It's known to be NP complete. And there are also other variants within graphs studied, like open neighborhood variant. Right now we are looking at close neighborhood variant. Okay, but that's just a note. Okay, so let's look at some results in the direction of the result that we are going to talk about in this talk. So consider a graph on n vertices and with maximum degree delta. So what maximum degree is basically, so you have the degree of a vertex is the number of neighbors it has in that graph, and maximum degree is maximum over all vertices, the degree of that vertex. Okay. So clearly delta is less than or equal to n, right? Because a graph on n vertices, in fact, delta is less than or equal to n minus 1, because a vertex can have at most n minus 1 neighbors. It cannot have itself as a neighbor. We are not, we don't think of self loops or anything. We are just looking at simple graphs. Okay, so delta is less than or equal to n. So the first result was due to Park and Tardos in 2009, which said that like the conflict-free close neighborhood chromatic number of a graph is order of log square n, which means it's at most some constant times log square n. And they also showed, so the result, this is all results from the same paper. They in terms of delta, they're getting log delta to the power 2 plus epsilon for any epsilon greater than 0. But if the minimum degree of the graph is at least log delta, so delta is the maximum degree. So if the graph has sufficiently large minimum degree as well, means every vertex has a degree of at least log delta and maximum degree is delta, then you can improve this upper bound to log square delta. You can shave off this epsilon from the exponent. And
Roger, so one question.
yes.
This is Amit Alok. Sorry to interrupt.
So
the first condition is just a general condition without degree requirement. So it just says that if you have a graph with n vertices,
exactly.
Oh, okay.
Yeah, the second one is a bound just in terms of delta. So you can replace delta with n because the delta is less than or equal to n.
Yes.
Yeah, but anyway, the first bound is better than that when you replace with n. Yeah.
Okay, thank you.
So yeah, so that's what I'm coming to the next bullet point. So you have this result due to Glebov, Szabo, and Tardos in 2014. They showed, I mean, this is in random graphs, they showed that there exist graphs with conflicts on n vertices. There is a graph on n vertices whose chromatic number times log square n. So it's a lower bound, or you have graphs which require log square n. Now this actually implies that there exist graphs which require log square delta, because delta is anyway less than or equal to n, less than or equal to n minus 1 to be precise. So this is the lower bound here. I mean, you cannot you cannot get better than log square delta upper bound. And what you have, the general upper bound is the second of these results, which is log delta to the power 2 plus epsilon. So you have this epsilon gap between in the exponent between the upper bound and the tight sample, or say lower bound. And we bridge this gap in our recent work. So we show that you can actually improve it to log square delta, and this is the best you can do. So the proof is quite easy to follow. Okay, I guess. So the next few slides are an outline on that proof, and then we look at some similar results which came very recently, maybe 1 month ago. Our results are maybe a few months old, in similar spirit, and then yeah. So that's the talk about.
Sorry, just
Yes,
couple of things. So is this lower bound is it constructive, or is this the probabilistic method?
It's random graphs. It's a random graph proof on random. Yeah.
And your result, so maybe I didn't fully understand it. So under what conditions is this order log square delta?
There is no. I mean, given a graph of maximum degree delta, its conflict-free close neighborhood chromatic number is some constant times, at most some constant times log square delta.
Okay. Okay. So without the min degree requirement.
Yeah, without the min degree, exactly. Yeah, we could remove the, yeah, flaws. Correct. Yeah. So any other questions? Yeah, so the proof is more graph theoretic. So I'll give an outline of the proof, and I'm pretty confident that most of you will be able to follow it because it's not.
Rogers, just a minor point here again.
Yes,
So
yes,
do the constants. So I guess you're using the lower bound from Glebov et al. So,
yes, yes.
yeah, the existence part, I mean, and so are the constants very different, or I mean, they just
For
is it
our
not something?
upper bound, the constant is like a small constant. I think maybe 10 or something like that, 4, 5, 10 or something. I don't remember exactly, but
Okay.
it's a small constant. Yeah.
Okay.
And for
And
the
this is an
load,
absolute constant, and it doesn't depend on any of except the delta. I think it doesn't depend on anything else.
no, it's just an absolute constant. It doesn't depend on
Just independent. Okay.
anything. Yeah. I don't remember the constant for Taldos's lower bound.
Okay.
Okay. Yeah.
Rogers.
Yes, sure.
Hi, this is Prasad Krishnan from IIT.
Hi, Prasad. Hi.
Yeah. So are there any bounds which use certain graph parameters which are not just the the maximum degree? So
Yes.
the kind of lower bound result which you are showing here is dependent only on one parameter. It looks like, right?
Yes.
And it's a existence result of some class of graphs which have this particular lower bound.
Yeah, the lower bound is on some random graph. Yeah.
Specific class of graphs. So it could very well be possible that there are other graph parameters
Exactly.
using which you can possibly.
So you gave me the opportunity to talk about some of our own other results. Sorry to say that. Yeah, but I'm just looking. I mean, there are many other results. So people have given bounds in terms of other graph parameters like tree width, upper bounds, and the upper bound in terms of tree width is, I think, still a multiplicative factor of 2 away from the type bound. Dr. Kalyan Sundara may be able to correct me on this. And then we had some bounds on path width, but that was a slightly different variant of this conflict-free problem, not on closed neighborhood. That was an open neighborhood. In closed neighborhood, there is Subruk, what are the other known bounds? Do you remember that? I think this neighborhood diversity and many other parameters, there were bounds, right?
There are bounds. So I'm just trying to think of a tree width since you mentioned it. So clear upper bound is.
Yeah. So just one note I can tell you: this open neighborhood variant is actually, if you get a bound for this open neighborhood variant, which I have not defined here, the closed neighborhood variant conflict-free chromatic number is at most 2 times the open neighborhood or something. So you get an upper bound for open neighborhood that also serves as a upper bound for closed neighborhood. So what I said was right. This tree width bound also works for closed neighborhood.
Okay.
And what other results were there? Subruk, maybe there was.
I think in terms of other structural parameters, there were due to others as well as due to like our own like the same set of authors in this paper. There are other graph parameters like tree width, other parameters like distance to distance to creeks. Then I'm just trying to recollect.
Yeah, there were some
feedback distance of the feedback vertex sets on the basis of size of feedback vertex set. Tree width, path width, etc.
So it's quite extensively studied, I would say.
And another class of graphs on which it is studied is various type.
Right.
Yeah. Just to add, another class of graphs instead of parameters like this is like graphs that arise out of like intersection of circles, like the picture Rogers showed at the beginning.
Which is closer to the application, like this one.
So unit disk graphs, then disk intersection graphs, and like square intersection interval graphs where the graph corresponds to the intersection between intervals. So there are it has been widely studied on the many geometric graphs like that, or graphs that arise in like geometric fashion like that as well. Yeah. Sorry. Go ahead.
Right. So the sense in which the lower and upper bounds are meeting here is in some sense a worst case among all possible classes of graphs. Right?
The lower bound is correct.
Right. Okay. Thank you. Yeah.
Yeah. Okay. Okay.
Yeah.
Okay,
So Rogers, sorry to interrupt again. Just one question. So, I mean, along the lines of what Prasad just mentioned.
Yes,
So,
please.
for random graphs, is it just an existence result, or can you show that for most random graphs? So, with high probability.
It was not shown for almost all random graphs or something. It was shown for, so that particular random graph model was not this GNP model that is commonly used. Here the vertices were partitioned into many groups, and the probability with which you put an edge between the between any two vertices in the ith and jth group was like some 0.9 to the power I plus j or something. So which means like if there are like and it was partitioned to roughly log n groups. So if you look at the first one or two groups, there you have almost every edge between them, because the probability is 0.99 to the power 1 plus 1 or 0.99 to the power 1. Whereas if you look at the last groups, the probability of putting an edge between them, any two vertices in them, is 0.99 to the power log n kind of. So it is sparse on one side and dense on one side, and that is quite sort of required, because this was also studied in GNP, where you won't get this lower bound. That was also established, because the degree has to be a graph where you have high degree as well as low degree vertices, and that is also that's it. Yeah.
Thanks.
That will be more clear in the last part of this talk, when the degree is sort of the graph, every vertex has sort of same degree, then you can get better bounds.
Okay.
Okay, so I hope I answered your question.
Yeah, thanks, Rogers.
Okay. So now let's go to this outline of this proof, which I promise is going to be very much followable. Okay, here we go. So we just defined this notion of maximal distance 3 plus set. Okay, in a graph. It's very intuitive. I think even the name suggests what it is. Like you take a subset of vertices, say capital A. We say it's a maximal distance 3 plus set if it satisfies these two properties. First one, you take any two vertices within A, say U and V. The distance between U and V is at least 3. I mean, that is there in the name of this, like we define it maximal distance 3 plus set, right? So which means distance between any two vertices within A. I mean, you take any path between any two vertices in U and V in A in the graph, that path has to be of length at least 3. It has to have at least 3 edges. That's the first property. Second property is that you take any vertex outside A. Okay. There should be a vertex inside A such that there should be a vertex U inside A such that distance between U and V is less than 3. I mean, that is also clear, because if the distance between distance of this outside vertex V to every inside vertex was greater than or equal to 3, then we would have added this outside vertex V to A, because it won't violate our first property. But right now we are looking at a maximal distance 3 plus set, which means that it's maximal. You cannot add any more vertex to the set A. The moment you add any outside vertex to the set A, the first property will be violated. Okay, so let's look at a picture here. I think that will make it more clear. So suppose let A be this maximal distance 3 plus set. Okay, and B be the set of neighbors of A. So B is the set of all those vertices which have at least one, I mean, they are the neighbors of the vertices of A. And C be the remaining vertices. Okay. Now, if you notice here, my A is a distance 3 plus set, which means that you take any two red vertices in the graph, you don't have a path of length less than or equal to 3 between any two red vertices. That's the first thing. And second property of this maximal distance 3 plus set was, you take any vertex outside A. Okay, they will be at a distance of 2 from some vertex in A. So if you look at this vertex where my mouse pointer is, it's at a distance of 2 from this red vertex. and therefore I cannot add this vertex to A. Okay. Similarly, this vertex is at a distance of 2 from A. This is at a distance of 2 from A. Now, if you take this vertex, it's a distance of 1 from a vertex in A. So you cannot add any more vertex to set A. It's maximal with respect to this distance 3 plus property. Now, such a thing has this following properties. Some observations we are making. First thing is that every vertex in B has exactly one neighbor in A. So can you see that? Suppose this vertex had 2 neighbors in A. Suppose it had 2 neighbors. Then those 2 neighbors are at a distance of 2 from each other. Right? So suppose this vertex in B had 2 red neighbors. That means that those 2 red vertices are at a distance of at most 2 from each other, which violates the fact, which contradicts the fact that A is a distance 3 plus set, right? Because any 2 red vertices have to be at a distance of 3 at least from each other. So that's the first property. Second property is that every vertex in C has at least one neighbor in B. Again, suppose this was not true. Suppose you have a vertex in C which had no neighbor in B. That would mean that you can actually go back and verify. If it had no neighbor in B, then it would mean that its distance to every vertex in A is at least 3, and therefore you could have added it to A. Okay, but A is already a maximal distance 3. It's maximal. You cannot add anything more to A. So which means you cannot have such a vertex in C. Every vertex in C should have at least one neighbor in B. And the third observation is that assigning the same color, which is basically red here, to all the vertices in A takes care of the vertices in A and B. By takes care, I mean, so now I have given red color to all the vertices in A. Now let's look at a red vertex. Is it CFCN colored or conflict-free close neighborhood colored? If you look at this red vertex in its close neighborhood, it is the only vertex which has red color. In fact, the other vertices are uncolored right now. If you look at this red vertex, it is the only vertex in its close neighborhood that is red in color. That is true with every vertex in A. Now let's look at a vertex in B. In its close neighborhood, it sees exactly one red vertex, right? That is basically the first observation here, because it cannot see 2 red vertices. So coloring all vertices in A with red color would imply that every vertex in A as well as B sees exactly one color in its close neighborhood. So I'm just pausing here. You can tell me what is not clear so far.
Roger, just one question. So when I define the neighborhood of a vertex, for example, in A, does the neighborhood include the vertex itself, or
in the name? So okay, in what context you are? Yeah, it's a close neighborhood. It includes the vertex itself plus the yeah. So we are studying this close neighborhood variant of this conflict-free color.
Yeah, sure.
Where you want some color to appear exactly once in the close neighborhood of every vertex.
Okay, close neighborhood. Right. Thanks.
Yeah. So you can see every vertex in A has satisfied what we are looking for, this property.
Yes. Yes.
Similarly, every vertex in B has also been taken care of. So the bad guys are basically these are the vertices in C, which do not have any vertex in its close neighborhood that sees. I mean, it's so these bad guys are vertices in C, which do not see, in fact, any color in its close neighborhood, let alone some color appearing exactly once. Okay. Now, at this juncture, I would like to tell something like, see, in our proof, we are not going to color all vertices. Okay, we may leave some vertices uncolored, but we will ensure this property that every vertex sees some color exactly once in its close neighborhood, or every vertex has some color appearing exactly once in its close neighborhood. We will ensure that. Now we may not color some vertices, but that's okay, because see, that is just a +1. Finally, at the end of the proof, if you have some vertices uncolored, you use some new color, let's say some golden color or something, and color all of them with that golden color. and still all its properties will be satisfied. So that way you will color all vertices and it's conflict-free close neighborhood colored, and you are using +1 color. So that's not going to affect the asymptotics. Anyway, our bound, we are only worried about this order of log square delta, right? Bound, that's what we are looking at, right?
So just to be clear, so does it mean that the number of vertices which will be left uncolored is a constant?
No, it can be it can be very large. Maybe it can be maybe half of the vertices of the graph are uncolored, let's say. But you color everything with a new color, with one extra color.
Okay.
Let's say you have not used the golden color so far.
Okay.
So all these new uncolored vertices, you give them golden color. So you're using only one new color.
Yes.
Right, but that will satisfy every. I mean, already the vertices have satisfied. I mean, they're proper. We have satisfied the desired requirement, right? Like every vertex is seeing some color appearing exactly once in its close neighborhood.
So, but does it mean that each of these vertices will appear in a different hyperedge? Sorry. I mean, so these can't form. So the vertices which are colored with this new color can't form a neighborhood in themselves.
Yeah, because even before we had colored them. Let's say they were white in color or something. I mean, you can also think they're white color. Yeah. So even before, like, let's look at this vertex. Like, if you can see my mouse pointer, this vertex at the top of B, it's seeing some vertex with red color, right? Exactly one vertex with red color. Now it has some other neighbors here which are uncolored.
Yes.
Let's say at the end of the proof, even at the end of the proof, these vertices are uncolored. I can give it a new color. Still this sees red color exactly once in its close neighborhood, right? That's what it wants.
Yes.
So I'm not going to tamper with already colored vertices.
Yeah. But I guess, I mean, so for example, I see that for vertices in B it's okay, but
We are anyway not taken care of. We will be looking at them.
Yeah. And anyway, yeah, I guess we can see more in the proof.
Yeah. So now we have these vertices in C which have to be taken care. A and B have been taken care. But now it's kind of obvious from here, because I mean, why not we repeat the same thing? Like, you only focus on this graph induced on vertices in C. You forget about A and B. And suppose you think this was the graph given to you, this G of C or something. Again, you can partition it into A dash, B dash, C dash, right? The same thing. So that's the proof idea. So let's go to the next slide. So this is the first graph, which is G equal to G0, which is given to you. You have this A0, which is a distance 3, maximal distance 3 plus set. B0 is the neighbors of the vertices of A0. And C0 are basically is the set of remaining vertices. And it is the vertices of C0 which do not see a unique color in its neighborhood, in its close neighborhood. We have to take care of them. What do? We now forget about A0 and B0 and look at this graph G1, which is G of C0. I'm only looking at this graph. My picture may not really illustrate that, but I'm only looking at this graph in the bottom picture. And that graph, I'm again partitioning it into 3 pieces. So you can think of this C0 being partitioned into A1, B1, C1 further, right? And so the A0 was given, all the vertices were given an orange color. A1, I'm going to give a new color, let's say blue color to all these vertices. That would mean A1 and B1 are taken care of. But remember, this A1, B1 are basically subsets of your C0, right? They are taken care of. Now you have this C1 left, which needs to be taken care. But you repeat the same procedure. The C1 here, you again divide it into A2, B2, and C2. Okay. And A2 and B2 are taken care by coloring A2 with, say, some new color. And C2 is left to be taken care of. You divide C2 into A3, B3, C3. You keep doing this. You keep doing this for, say, some K rounds where K equal to this number 4 log delta. It can be anything greater than 4. You can put 100 log delta or something. But again, the constant that we get in the bound may get bad. That's all. Maybe bad. So you take some roughly 4 log delta rounds. You keep doing this. And now you have what is left to be taken care is basically this CK, vertices of CK, right? So you first took care of A0 and B0. C0 was left as vertices of C0 we had to take care of. We divided it into A1, B1, C1, and A1, B1 were taken care by the second round of coloring by giving a blue color. Now C1 we divided it into A2, B2, C2. Now A2, B2 we took care of by another new color, giving the vertices of A2 with another new color. So C2 is left to be taken care of. So we kept doing this until we reached this stage, the kth stage. The k is, say, some constant log delta. So as noted here, at this point, the only vertices which do not have a color appearing exactly once in their close neighborhood are vertices of Ck, right? But now you look at this property, the second property. We have not made use of the second property here of this ABC set, ABC partition, which says that every vertex in C has at least one neighbor in B. Okay, I mean that's because A is a maximal distance. You can actually verify that. But so you take for the time being, you take this property for granted that it exists. It's there. So every vertex in C has at least one neighbor in B, which means every vertex in C0 has at least one neighbor in B. But C0 I partitioned into A0, A1, B1, C1. Now every vertex in every vertex in C1 has at least one neighbor in B1 and B0. Now this C1 I partition it into A2, B2, C2. Every vertex in C2 has at least one neighbor in B2, at least one neighbor in B1, and at least one neighbor in B0. So finally, when you reach here at the kth stage, every vertex in Ck has at least one neighbor in Bk, at least one neighbor in Bk minus 1, at least one neighbor in Bk minus 2, up to B0. I hope this is clear. It's just I'm repeatedly applying that second property. So you can stop me. I can explain it again if this is not.
Sir, how to choose this set in a graph? Like, first we need to choose this A node, B node, and C node. So from where do we will start in a graph?
Yeah,
it will be given to us.
That is kind of straightforward. You just take one vertex. Let's say you take a vertex V1 into your A naught. Now all neighbors of V1, none of the neighbors of V1, you do a breadth first search from V1. You know what a breadth first search is, right?
Okay, yes, sir.
So you take the neighbors of V1, you forget about them because you cannot put any of the neighbors of this vertex V1 into your set A0. You have already put V1 into A0.
Okay.
Now the neighbors of its neighbors also you cannot put because they are also at a distance of 2 from V1. You need to put somebody at a distance 3 from V1, right, into your set A0. Yes. Now you go to the neighbors of neighbors of neighbors. If there is somebody there, you put that guy in your set A0. Now you have two vertices in A0, let's say V1 and V2. Now you do a search from V1 and V2 probably. I mean, you look at all vertices which are neighbors of either V1 or V2. Then you look at vertices which are neighbors of V1 or V2. And then you look at vertices which are neighbors of neighbors of neighbors of V1 or V2. And from there you can pick somebody and put it. Yes. So you keep doing this until you cannot do any further.
Okay.
And that you can get a not so difficult algorithm. What could be the time complexity? Maybe quadratic. Yeah.
Okay.
Yeah. Okay.
So I guess so this implies that. Yeah, Prasad, please continue.
Sir, okay. So I have one question.
Yes.
Not about this algorithm as such. Just about this conflict-free coloring. So let's say that you are trying to do a conflict-free coloring, close neighborhood coloring.
Yes.
And is there any, so how do you put it? So is there any bound on the number of colors which will appear in a close neighborhood in any conflict-free coloring?
Well, I don't think that has. I don't know whether that has been studied. I don't know whether people were really. Well, of course, the total number of colors used is certainly a bound on the number of colors that appear in a given hyperedge, because you're not.
That's upper bound is fine. So lower bound is what I'm thinking of.
So within a given hyperedge, is it how many colors will appear?
Correct. Yeah.
I'm not clear about the question. You want it like how many colors appear in each given hyperedge? Is it you want a lower bound to that? You want a lower bound to the
Correct.
maximum
exactly.
of that.
Is there any known result?
Not to my knowledge.
Or do you have example where?
Whether that would that be interesting to the this wireless communication community?
Yeah, maybe. So maybe I have some problem which I'm
Let me
thinking
go back
about
to this
changing.
picture here. So you are basically asking.
Talk to you after the session.
Yeah, so you're basically asking within a hyperedge, the number of colors appearing, is there a lower bound to it? Is that what you're asking, right? Here in this particular 1, 2, 5, there are 2 colors appearing, red and blue.
Right.
Okay, so that may have some application, is what you're.
Yeah, exactly. Yeah.
Okay.
So, I mean, is the question for
sorry to interrupt again. So your question, I'm just trying to understand the question better. So do you want to, like, each hyperedge should have some minimum number of colors? Is that the goal?
No. The minimum it is, the better it is, I would say. Like.
So you want to minimize the number, okay?
I'm just putting a question. I don't know exactly if there is a. I mean, that would be the harder thing to do, right? So if I had the, if I had to do a conflict-free coloring where every color in the hyperedge is different, that would be a sort of easier case, perhaps.
Okay, you want each hyperedge to use as less number of colors as possible, is what you're saying, right?
Yeah.
Okay. I'm just trying to understand the problem here.
Okay.
Yeah, I don't know if this helps, but this is Amitabh. I was just, sorry to interrupt again. I was just thinking, is it like this Ramsey theory kind of question where you want to start out with a set of colors and you want to, I mean, I'm not just thinking. So you have a particular kind of conflict-free coloring that you want, given a particular set of colors, and you're interested in how large the graph should be.
So Ramsey theoretic questions, to my understanding, is that you cannot avoid such certain patterns, is what they are about, right? I mean, no matter what you do, you cannot avoid certain patterns. Here we are trying to bring some patterns, right? You're trying to.
I'm not sure, but the kind of question Prasad's thought was kind of it seemed to have that
perhaps it is Ramsey theoretic. So the question which I am asking is, yeah.
Oh, you're okay. You are asking no matter how you
given
color.
that you want to do a conflict-free coloring.
Yeah,
that's right.
Exactly.
That's right.
You're given a conflict-free coloring, and I guess a few number of colors, and you want to see how large the graph should be to even, or what is the minimum size of the graph which will allow you to even think of a conflict-free coloring with that sort of a.
Okay. So the question is something like you are doing a conflict-free coloring, and then a certain minimum number of colors is something like inevitable. I mean, that many colors will appear in a hyperedge or something, right?
Yeah.
So that is what
exactly. Yes.
The classic Ramsey theory requires you are expecting independent sets and clicks, right? If you want, to find a thing, so that means the size, the graph should be at least so big to even hope to find something like that.
Yes.
Correct.
So Prasad's question looked like that flavor. You want to, given the set of colors and conflict-free nature, how large should the graph be?
Okay. Yes.
Okay, so just something that maybe you can think
Yeah,
about.
Given your figure, right, it suggests that it may actually have a practical application. I can't think of it right now, but the figure you had in slide 2 or 3 was quite nice.
Oh, okay. To be honest, at least for me, practical application is a farce. But
exactly. But if you want to sell it, it does seem to have a meaningful thing.
Yeah.
Sorry about the interruption. Go
on. No problem. Okay, so coming back to, so we have reached this point, this crucial point where we have done this k times the same thing, like 4 log delta times k equal to, or let's say some 100 log delta times or something. And what we just said is that the second property ensures that every vertex in Ck has at least one neighbor in Bk, at least one neighbor in Bk minus 1, at least one neighbor in Bk minus 2 up to B0. Okay, so at this point, we're going to use a known result on hypergraphs, and that will just give us the proof. Okay, So if you notice, we have done 4 log delta rounds, right? K equal to 4 log. So we have only used 4 log delta colors so far, because at every round you are using a new color. Like here I used yellow, blue, red, and so on. So we have only used some constant times log delta colors. We can use constant times log square delta colors. That's the proof. That's the bound we are attempting. And that's all you can get also. So if CK is an empty set, we are done. I mean, which means every vertex has been taken care of, because it's only the vertices of CK that needs to be taken care of. But suppose it's not an empty set, and that's only when we need to do something. So we construct a hypergraph in the following manner. You take a vertex. As I said, this notion is defined on hypergraphs, right? So my vertex set of the hypergraph is basically B0 union B1 union B2 union up to Bk. All these central pieces, like if you go to the previous slide, the central pieces. And what I said just now is that every vertex in CK has at least one neighbor in BK, at least one neighbor in BK minus 1, and so on, right? You look at the neighbors of, you take a vertex in CK, you look at its neighbors in BK, its neighbors in BK minus 1, its neighbors in BK minus 2 up to B0. All these neighbors together form the first hyperedge. So you take a vertex V in this CK, the top vertex, call it V. Its neighbors in BK, union its neighbors in BK minus 1, its union its neighbors in BK minus 2 up to B0. They form the first hyperedge of this hypergraph, SV. Similarly, I take the next vertex, let's say W in CK, its neighbors in BK, its neighbors in BK minus 1 up to B0, form the second hyperedge of this hypergraph. Okay. So I've written it down here. So you have this hypergraph where the vertex set is all these central portions, B0, B1, union, BK. And the edge set or hyperedges are basically the neighbors of this CK, vertices in CK in these central portions. Now, since K is log delta, 4 log delta, and every vertex has at least one neighbor in BK, at least one neighbor in BK minus 1 and BK minus 2 and so on. So these hyperedges are going to be of size at least 4 log delta. Right, SV is my hyperedge corresponding to a vertex V in CK. Because they have, every vertex has at least one neighbor in BK, at least one neighbor in BK minus 1. So every hyperedge is of size at least some constant times log delta. And second property, which I would suggest you can go back and maybe verify, is that every hyperedge intersects at most delta square other hyperedges. So what are my hyperedges? You take my first vertex V in CK, its neighbors in BK, its neighbors in BK minus 1, BK minus 2, the union of all that, right? And you take the second vertex W, its neighbors in BK, BK minus 1 and dot form the second hyperedge, and so on. So these hyperedges, you take any one hyperedge, it is intersecting at most delta square other hyperedges. That's something which I suggest you can right now take it as a black box, but it's quite straightforward to verify that. Now, once you have these two nice properties, we're going to use an existing result which will give us. So we want to show that this hypergraph H prime has a conflict-free, we can color it in a conflict-free fashion using log square delta colors, at most order of log square delta. And that will be the proof, because it is only these CK vertices that we need to take care of. And if we color this hypergraph, which are basically the neighborhoods of the vertices in CK, in a conflict-free fashion, that is every hyperedge seeing some color exactly once, that would mean every vertex in CK would see some color exactly once in its neighborhood. So we have to show this hypergraph has a conflict-free chromatic number of order of log square delta, but this is a known result. It follows from this result of the first paper that I cited of Park and Tardos, which says that it's a general result on hypergraphs. If every hyperedge is of size at least 2t minus 1, and if every hyperedge is intersecting at most gamma other hyperedges, then its conflict-free chromatic number is, this is the most general bound in this domain, in this problem. So it's t gamma to the power 1 by t log gamma. Now for us, this t is the size of a hyperedge, which is at least 4 log delta. So 2t minus 1 is at least 4 log delta, or t is roughly 2 log delta. And your gamma, which is basically the number of hyperedges in which this hyperedge, a given hyperedge is intersecting, for hypergraph H prime is delta square. So gamma is delta square and t is 2 log delta. If you plug in these numbers in this bound, you get the conflict-free chromatic number of this hypergraph H prime to be, or H dash to be order of log square delta. And once you color H prime, this hypergraph H dash in a conflict-free fashion, you have taken care of the vertices of CK. They are seeing some color in it's exactly once in their neighborhood. And there may be some vertices which are not colored. As I said, you can use an entirely new color to color. So this completes the proof. I hope this was clear. So any questions so far?
So hi, this is Manoj here.
Hi.
So the only place where you're possibly using the fact that delta is the max degree is that part, right? Where you have the part which you said like can go and verify like delta. That hypergraphic CK has like delta.
Yeah, this part I need. Correct. Yeah, this part needs that it uses the fact that this property B at the bottom uses the fact that the degree of maximum degree of this graph is delta.
Because in no other part you actually use that so far.
Okay.
Right?
Yeah, I think
the rest of the proof I don't think it has appeared.
Yeah, it's not really required. Yes.
This is the part where the maximum degree is coming.
Yes. I think you're right. Yeah. Yes. I cannot immediately think of any other place where we are using this maximum degree. Okay, so that completes the proof. So how many minutes I have, Shashank?
It's actually around 4:30 now. I mean, you can take maybe 5-10 minutes.
Maybe I'll wind up in 5 minutes. Maybe I'll just mention about the other result.
Sure,
and then outline in one slide and then we'll wind up.
Sure.
So we have, so our result combined with the lower bound says the following, what is highlighted in bold, which says the extremal value of the conflict-free chromatic number of graphs with maximum degree delta is theta of log square delta, which means you have an upper bound which is some constant times log square delta. You also know of graphs which require some other constant times some log square delta, right? So extremal value, by extremal value I mean that you take graphs with maximum degree delta. You take all graphs with maximum degree delta, and you find the conflict-free chromatic number, close neighborhood chromatic number of each of these graphs whose maximum degree is delta, and the maximum of all that. That's what you call the extremal value of the CFCN chromatic number for graphs with maximum degree delta. So we have established that is like some theta of log square delta. It's tied from either sides. Right? Okay. Now, just one observation which I had actually mentioned a bit about that random graph earlier, which Labo, Sabo, and Cardos are using. So the expected degree of vertices vary from 1 by n to the power 0.9 to n by log n. So 1 over n to the power 0.9 to n over log n. So that is, and I think also I mentioned that this lower bound that they got will not work, or you won't get a similar lower bound for classical GNP random graph. That is also a known fact. So you need this graphs where at one end it is sparse and the other end it is dense. So the degree is varying, like swinging from a very small number to kind of high degree vertices. You have both, and it is for those graphs you have this tight, which require this log square delta. So naturally you ask this question: what about graphs that are delta regular? Delta regular means that every vertex has degree delta. Okay, what about graphs that for which every vertex has degree delta? So to this end, so this was shown in 2012 by Kostochka, Kumbat, and Isaac. So they showed that if the graph is delta regular, you can get an order of log delta bound. So the general bound is order of log square delta, but you can improve to get an order of log delta bound if the graph is regular. And in fact, very recently, this was extended to even near delta regular graphs by Debsky and Prisblo, I think. This is a paper which came in arXiv last month, I think. So they extended this result. So what do we mean by near delta regular? So the first statement requires that every vertex in the graph has a degree exactly delta. But the second statement says that you can actually relax it a bit. You can say that there are graphs with degree, I mean, the minimum degree is at least, say, some 1 by 100 delta or something. Some alpha delta, where alpha is less than 1. So every vertex, its degree varies from alpha delta to delta. They are near delta regular graphs. So the degree varies from alpha delta to delta, where alpha is some number less than 1. So even for near delta regular graphs, you can get the same bound, order of log delta bound, which is an improvement over the general bound, which is order of log square bound. Now this bound also, due to some lower bounding result from the same paper, the second paper, is tight. You cannot get better than this. Okay, so I have a couple of slides on that. I have basically 3 slides on that, and that will come. That will be the end of the talk. But I will skip the second and third slide. I'll just do this first slide, a proof idea in 2 sentences, and we'll finish.
So maybe just to go back to that previous slide. Yes. So here, when you say the extremal value, you're also maximizing overall possible delta, because
no, you take all graphs whose degree is at least alpha delta, and maximum degree is delta.
Sure.
You take all such graphs in the world. Minimum degree is alpha delta and maximum degree is delta.
Okay.
You find conflict-free close neighborhood chromatic number of each of these graphs and find the maximum of that.
Okay.
That will be log delta.
So, but the lower bound that you have here is for a line graph for n vertices, right? So
yes, but n is again, you can replace by delta, right, for lower bounds, because delta is less than or equal to n or something.
Yes, but even so, if I fix a delta, which is something maybe like log n, do I still have a lower bound of this form?
Fix a delta, which is
so let's say that I fix a delta which is a constant fraction.
Okay. So that yeah, you can.
So delta grows in some fashion with n.
Yes, you still have a lower bound, because this lower bound is basically for line graphs of complete graph on n vertices. Now I will answer that question in 2 sentences possibly. Sure. So for this complete graph on n vertices, when you take its line graph, its degree is basically 2n minus 2, I think.
Okay.
It's a 2n minus 2 regular graph.
Okay.
It's a it's a 2n minus 1 regular, 2n minus 2 regular graph. Okay. So whatever, 2n minus 1 or 2n minus 2 regular graph. Now you take any, this is true for every line graph, this lower bound.
Okay.
So for any n, you can get that bound. So if you want, say, your delta to be 100, then you take some complete graph on 50 or 51 vertices or something. Okay, so 2n minus 2 will be 100.
No. So I guess my question was, so let's say I want a sequence of graphs of on n vertices where my degree grows as, say, log n. So can you construct graphs of degree log n on n vertices for which the conflict-free chromatic number is?
That is not known. Please.
Okay.
Yeah.
Okay.
Yeah. So here the graph. Yeah. Here actually this line graph has roughly n square vertices when you go to line graph, and the degree is n. Yeah. Your question is basically, so degree is basically square root of the number of vertices in this graph.
Correct.
But you are asking what if degree is, let's say, log of the number of vertices? Can you again get similar bound, right? Correct. That is not known, at least to the best of my knowledge.
Nice.
So I'll just finish. This is my last slide.
Sure.
An outline of this proof. So this proof, maybe you can read that. It basically, if the graph is near delta regular, the first statement is true for any graph. It's, I mean, irrespective of this conflict-free setting. This is a general graph theoretic property. You can randomly select a subset of vertices V prime such that every vertex in the graph has nearly log delta neighbors in it. Has some constant times log delta, at least C1 log delta and at most C2 log delta neighbors in it. You can get some set V prime like that. Okay. Because the original graph is near delta regular, then you can get a subset of vertices such that every vertex has near log delta neighbors into that subset. And then the second property is, now you randomly color that subset V prime with roughly some log delta colors or some constant times log delta colors. And then you can show that the probability that this is a conflict-free coloring is greater than 0 or something. So it's a probabilistic proof. So that's the outline of this proof of this recent paper. And I actually had 2 slides, but I will skip that. We'll skip that. Even that does not convey much. Yeah. So.
Yeah.
Thank you.
Thanks a lot, Rogers, for a great talk. Any questions from the audience?
I have one question.
Yes. Yes.
You spoke about this conflict-free closed neighborhood coloring, right?
Yes, yes.
So what results are known for the general conflict-free coloring on hypergraphs?
The general conflict-free coloring on hypergraphs, this is sort of the best result known, that the most general result known. This theorem, that can you see this theorem? This.
Yeah.
Let me make it full screen here.
So this is for.
Yeah.
Okay, so
another result known is that if you are given a hypergraph where every vertex or every point is present in, let us say, at most delta different hyperedges, then its conflict-free chromatic number is at most delta plus 1 or something. Or let me not use delta, let me use some other letter, alphabet, let's say D. A point is present at most D other hyperedges. So you are given a hypergraph where every point or every vertex is present in at most D other hyperedges, then the conflict-free chromatic number of that hypergraph is at most D plus 1. That is another result known. And there are maybe, yeah, I mean, I think that these are the 2 most popular results known.
Okay, thank you. One more
Yes,
question. So in your in the style of this close neighborhood type colorings.
Yes, yes.
Suppose the maximum degree is equal to n minus 1.
Okay.
Then is my understanding correct that this number would exactly be equal to just 1?
Yeah, I think you have a universal vertex there, right?
Right.
Then you can give that universal vertex some say red color, and every other vertex may be blue color.
Okay, so 2. It will be 2.
Maybe 2, I think. Can you do it in 1? Maybe. Yeah.
Yeah, if you leave vertices, if you allow to leave vertices uncolored, then yeah, 1 is possible.
Yeah, 1 is possible. Yes. Yeah. If you want to color every vertices, then maybe 2.
Yeah.
So that sort of suggests kind of a extremal quantities for this degree would give small colors for small number of colors for a conflict-free coloring, right? If delta is too small or too large, then you would have this number to be very small. Is that correct?
Delta is too small, then this number will be small from our bound or these bounds.
Right.
And sorry. And when delta is large, yeah, correct. Even when so Subruk, even if it's not universal vertex, a near universal vertex will also make
Yeah, that's what I'm thinking. Yeah, that seems to help also, right? Because
that may also help.
you can address a lot of vertices through this near universal thing.
Yeah, then you only have to worry about the remaining guys. Yeah,
Correct.
that may make it easier. Yeah.
Right. So in your picture, whatever you have like A, B, and C vertices, it is as though the set C is of very small size, basically.
We can't really say that, right?
Just to show, maybe it looks like visually it may look like that.
Oh, visually it may.
No, is that the question?
Okay, can you
in the setting that there is a node which has a large degree. If I just put it in AK, or
Correct,
if I just put it in A0.
Okay.
Right. Right. So what he's saying is, if there is a large degree vertex, if you put it in A, then most of the vertices will come.
Yes. Okay. Oh, you're right. Yeah.
Right.
Yeah. So, okay. So this proof is, proof is internally taking care of that, or what to say, not internally is the right word, implicitly taking care of that, right? Probably. So if we use this heuristic that while constructing A0 or A1, we start by taking large degree vertices first or something.
Yeah, I guess.
Yeah.
I guess in your proof you are never using any properties of A0, right? I mean, so as in the size of A0.
Yeah, not really. Yeah, so we don't really care how it is constructed, but yeah, maybe for some special graph classes or something, what Prasad was suggesting may help. Like you start taking the high degree vertices, and if there are some high degree vertices, maybe you can say that size of C0 is considerably small or something, and then thanks for saying that. Thank you.
Probably the number of steps you require could be much smaller for.
Yeah. But I didn't think of this. So I hope at least some things were followable. Yeah, I hope it was.
Yeah, it was great.
Of course, I mean, given the number of questions you got, I'm sure that's a very good indicator.
That can be either way.
Actually, I'm sorry, so I'm going to take the opportunity to ask another question here, if you don't mind.
Sure.
So at the end, you mentioned the line graph idea, right? And okay, I'm not from this area, so this question may be a little silly, but let me take a shot at it. So
please.
In some sense, if you think, the way I understand edge coloring and vertex coloring, they can be seen as duals via some kind of line graph constructions. So I was wondering if, this is the object I have come across in coding theory, where what we generally want to do is you give me a particular code, right? We can construct certain graphs, and then we somehow care for edge colorings, which indicate if two code words are close. So I can have this notion of approximately equicoupled codes, where I look at pairs of code words and see if they satisfy some distance condition. Now, is there a notion of conflictly coloring for edges which is meaningful? And I'm just coming from that. I'm not thought deeply about it.
We do have one notion which we also have some results on that, and there's also this other paper that I talked about. Basically, here in the second line, they also talk about this edge coloring variant, where they have a bound of log n sort of. Again, that was an open neighborhood variant, but yeah, let me define the problem there. Okay, the bounds come second, right? Okay, so you have you take any edge, and if you are looking at the close neighborhood of that edge, it means that, let's say your edge is AB. You look at the other edges which are incident on A, and other edges which are incident on B, and this AB edge itself, they together form the close neighborhood of AB.
Yes.
And then you can ask the same question. I want some you're coloring edges and some color appearing exactly once in its close neighborhood. Yeah. So we also did, we had the other work where we had many other results, where we also had this one result on this, but we don't really know of any practical application to that. So it would be great if you can tell us something where there's some practical relevance to that question on edges.
Okay, actually, so this is something off the top of my head. This is how we use at least the edge coloring idea.
Okay.
So it seems like there is this notion of so in generally coding theory we look at what is called unique decoding. So you want to basically build a code book, use that to communicate a message reliably and uniquely in some sense.
Okay.
But oftentimes people look at a generalization of this, which is what is called list decoding. And so if you start building structures for lists, then hypergraphs are the natural generalizations.
Okay.
So the object I cared for in our work was basically you were trying to find, if you give me a particular code, which means a collection of vectors, we were trying to extract out pairs of code words or triples or four tuples of code words, which essentially were having some kind of a common property. So we were looking at some kind of clicks of certain graphs and so on. So that's where I'm coming from. My limited, but it seems like the conflict free thing would also be meaningful in this setting. What it is, I'm not quite sure of as of now. But perhaps list decoding is a very old problem in coding theory. It's been looked at since the 60s, and I'm sure there will be a version of these kind of objects which might be of interest there.
Okay.
That's really just. I'm not quite
maybe Subru can maybe tell a bit more about this. I mean, I just.
I'm sorry, I didn't quite pay attention to the question.
No,
sorry.
I was just saying the problem I asked Rogers was about whether you could have the edge coloring version of CFCN, and Rogers mentioned that you have looked at it. So, in case you're looking for practical application, I know that it's not something important, but in case you are interested, then maybe this object called list decoding might be useful. It comes in coding theory quite a bit. And
I have heard of this decoding.
Yeah, it was something some object which I should be interested in. Not sure, but
right. I think there are some computer scientists who have worked on like variants of this decoding itself, this decoding itself.
Yeah. In fact, coding theory is of interest to theory CS guys, and that's a national.
Yes.
But again, this is just very vague thoughts. So in case you find it useful, you can definitely look it up.
Yes. Okay. Thank you.
Yeah. Thanks.
Right. Any other questions? Okay, so if not, maybe let's thank Rogers once again.
Yeah, thank you. And thank you for the questions. I think we had Subruk, I think we had more questions in this talk that I think this talk we gave in another graph theory forum. I think we had a lot more questions here than what were asked.
That made it very interactive and interesting. Yeah.
I think you really mean that theory matters.
Yeah, it certainly matters to us, and it was a very accessible and fantastic talk. So thanks.
Thanks a lot. Yeah, so for the audience, I guess the next talk will be sometime in December. We'll intimate the details soon. So stay tuned.
Yeah, and in case you're not already on the, so you
Thank
can
you.
join our
Thanks, Rogers.
mailing list. Please join.